So a rational function is any function where you have one polynomial, p of x, in the numerator, divided by the denominator polynomial, and typically when we have a rational function we would encounter problems in the sense there are certain values where the function will not exist. So we have to exclude those values from the domain of the rational function. Finding those values are very easy. All we have to do is set the denominator equal to 0, for instance, and that function set x minus 5 equal to 0 and solve for x, which would imply x is equal to 5. So the domain must not include 5. So in set notation, it's x is all real numbers except 5. And in terms of an interval notation, so we have all values, all real numbers, from negative infinity all the way up to 5, but we cannot include 5, so we put a hole, an open dot, and go all the way up to positive infinity. So we should not be including 5 in the domain. So the interval notation would be negative infinity all the way up to 5, union 5 all the way up to infinity, and as you can see that I'm not including 5. In a similar manner, we want to find the domain of function g of x, so we set the denominator equal to 0, and solve for x, so which would mean x squared minus 25 equal to 0. That would imply x squared equals to 25, which would mean x is plus or minus 5. So in terms of set notation, all x values that are real numbers except x equals 5 and x equals negative 5. In terms of interval notation, this would be negative infinity all the way up to negative 5. We cannot include negative 5. Negative 5 up to 5. We cannot include 5. And 5 up to infinity. The U stands for union. So in part C, we have x plus 5 over x squared plus 25. And if we set the denominator equal to 0, there is no number, no real number that you can plug in for x would make x squared plus 25 equal to 0. So the domain has no problems whatsoever. So in terms of set notation, x would be all real numbers. And in terms of interval notation, it's negative infinity all the way up to positive infinity. So there is this concept of right limit and left limit. So the arrow notation, as you can see here, x approaches 0 and superscript negative. So that would mean x approaches 0 from the left. Likewise, there we would interpret it as x approaches 0 from the right. And there we simply say f of x approaches infinity. And here we would say x approaches negative infinity, in the sense it is decreasing without bound. So over there, x approaches positive infinity, in the sense the value of x increases without bound. So over here, when f of x is approaching infinity, the function value increases without bound. In other words, the y value increases without bound. Likewise, if we say the function values, if f of x is approaching positive infinity, they are referring to this particular graph. So it's increasing on this side, it is going up, and it is increasing on that side. So it is increasing without bound on both sides. However, I would write a side note here, that's where I was going. That would mean the function values are decreasing without bounds. So anytime we have a point where the function is approaching infinity or negative infinity, we end up having a line called a vertical asymptote. The vertical asymptote is an arbitrary vertical line, so which is why we have it as a dotted line. So it is arbitrary. And the function moves along the arbitrary line either toward positive infinity or toward negative infinity. So the behavior of the function is not the same on either side of that arbitrary line, the dotted line. For instance, when we approach -3 from the left, the function is going toward negative infinity. However, when we approach it from the right, the function is going toward positive infinity. So, as we approach negative 3 from the left, we write it as x is approaching negative 3, and the superscript indicates from the left. The function is going toward negative infinity. Likewise, when we approach negative 3 from the right, that plus indicates from the right. The function approaches positive infinity. In a similar manner, we have 1 as we approach 1 from the left-hand side. The function is going down toward negative infinity. As we approach 1 from the right-hand side, the function is going up toward positive infinity. So there is a dotted line on the x-axis, which is y equals 0. And what happens as the value of x keeps on increasing? So as x gets larger and larger, the function is dipping down toward 0. And the same happens on this side. It is getting closer and closer to 0. So as x increases toward positive infinity, the function becomes 0. In other words, as x gets larger and larger, a bigger positive number, the value of the function becomes 0. If x gets smaller and smaller, in other words, it's going toward the left, the function is going toward 0. So how do we find a whole and a vertical asymptote at some x is equal to a? So first step is to get rid of the common factors in a rational function, because we are dividing one numerator polynomial by the denominator polynomial. So the chances are something is going to get cancelled. So, but not always. So we have x plus 2 over x squared minus 4. I could write it as x plus 2 times x minus 2. The x plus 2's would go away. We have 1 over x minus 2. So set denominator equal to 0. And solve for x. This would imply x minus 2 equals 0, so x equals 2. And that is the vertical asymptote, because if you draw a line through x is equal to negative 2, that would be a vertical line, and this is an arbitrary line, so we draw it as a dotted line. The whole is at 2, because the domain would go from negative infinity to 2. We cannot include 2, union 2 to infinity, which would imply the whole is at x is equal to 2. The next problem, as you can see, there are no common factors between the numerator and the denominator. Nothing to cancel here. So we simply set denominator equal to 0. And solve for x, which would imply x times x plus 5 equals 0. So there are two factors that would imply x is 0 or x plus 5 is equal to 0. So that is our first vertical asymptote. The second vertical asymptote is x is equal to negative 5. So the domain starts at negative infinity, goes all the way up to negative 5. We cannot include negative 5, so union, negative 5 up to 0. We cannot include 0. Union, 0 up to positive infinity. So the holes are at x is equal to 0 and x is equal to negative 5. So in part C, there are no vertical asymptotes because there is no real number that would make the denominator 0. So if there are no vertical asymptotes, that would simply imply that there are no holes. So now that we looked at vertical asymptotes, we can move on to horizontal asymptotes. So a horizontal asymptote is a horizontal line, an arbitrary line of that sort. So sum y equals b, or y equals negative c, and it is a line along which a function goes toward infinity that way, or it could go that way, and so forth. So how do we recognize the presence of a horizontal asymptote? So we're dividing a polynomial by a polynomial. So we have an nth degree polynomial and an mth degree polynomial. So the power is n here. And m there. If the numerator degree is less than the denominator degree, then the horizontal asymptote is always y equals 0. So the numerator degree is less than the denominator degree. But on the other hand, if they are the same, if n is equal to m, all we have to do is divide the leading coefficients of the leading terms. So we'd simply do a divided by b, set it equal to y, and that would be the horizontal asymptote. However, if the numerator degree is greater than the denominator degree, there will be no horizontal asymptote. So in the first example here, the numerator degree is 2, the denominator degree is 2. They are the same. That would indicate no horizontal asymptote. In part B, the numerator degree is 1. the denominator degree is 2, so the denominator degree is bigger than the numerator degree, so the asymptote oh, I'm sorry, I kind of messed up here. Going back, so the numerator degree is equal to the denominator degree, so we divide the coefficients, which is 15 over 5. I apologize. So 15 over 5, we get 3. So the horizontal asymptote is y equals 3. So the asymptote, the horizontal one in part B, would simply be y equals 0. And the last case, the numerator degree is 2. The denominator degree is 1. The numerator degree is greater than the denominator degree, so no horizontal asymptote. Perhaps you might have thought when I was doing part A that I was doing something wrong, and if you recognized it, that is actually a good thing. So a slant asymptote is an asymptote that is diagonal. It kind of goes that way. The line in red is the slant asymptote. Slant asymptote is it's also known as the oblique asymptote. So a slant asymptote is a line, hence the form y equals mx plus b, occurs when the polynomial in the numerator is higher than the polynomial in the denominator. But earlier I said, oh, there is no horizontal asymptote if the numerator degree is bigger than the denominator degree. So the key word here, or the key phrase here, is no horizontal asymptote. We are not mentioning, or we're not saying anything about a slant asymptote. So a slant asymptote happens if the numerator has a higher degree than the denominator. So a slant asymptote happens if that numerator degree is bigger than the denominator degree by exactly 1. In the sense, if the numerator degree is x cubed, the denominator has to be x squared. And if the numerator is x squared, the denominator has to be x. So exactly 1 degree higher than the denominator. So the numerator has to have a degree exactly 1 unit higher than the denominator. So the function f of x will certainly have a slant asymptote because numerator degree is 2, denominator degree is 1. So how do we go about finding a slant asymptote? We simply divide the numerator by the denominator, then throw out the remainder. So since the denominator is a factor of the form x minus 2, we can use synthetic division to find the slant asymptote. So let's go ahead and do that. The numerator polynomial has coefficients 2, -5, and 7. The denominator has a factor x minus 2, which would imply 2 goes here. The process of synthetic division states we bring the 2 down. We multiply 2 and 2 to get 4. We add -5 to 4, we get -1. 2 times -1 is -2. We add 7 and -2 to get 5. So what is the slant asymptote? It is y equals m would be the first coefficient, so 2x, and b, the y-intercept, would be the second coefficient, -1. So there are steps that are involved in graphing a rational function. These are 7 steps. So first we determine symmetry, in the sense we want to know if f of minus x is equal to f of x, which would imply even symmetry, and f of minus x is equal to minus f of x. That would give us odd symmetry. And we have to find the y-intercepts and x-intercepts, of course. We find the vertical asymptotes, we find the horizontal asymptotes. If there are no horizontal asymptotes, we find the slant asymptotes, but keep in mind the slant asymptote happens only if the numerator degree exceeds the denominator degree by exactly 1. And then finally we draw the asymptotes, then plot a few more points. So here is the graph, it's at the very bottom. So let's determine symmetry. So f of minus x is 2 times -1 squared divided by -1 squared. Sorry, don't know where I got that 1 from. 2 times minus x squared divided by minus x squared minus 9, which gives us 2x squared over x squared minus 9, which is the same as f of x, so we would have even symmetry. In other words, we are symmetric about the x-axis. Excuse me, the y-axis. So we know how to find the y-intercepts and x-intercepts. So to find the y-intercept, we set x is equal to 0. So f of 0 would be 2 times 0 squared divided by 0 squared minus 9, -2 over 9. The x-intercept is found by setting y equals 0. In other words, f of x is equal to 0, which would imply 2x squared over x squared minus 9 equals 0, which would imply x is 0. Are there any vertical asymptotes? How do we find the vertical asymptotes? We simply we simply set the denominator equal to 0 and solve for x, which would imply x squared minus 9 equals 0, x squared is equal to positive 9, x would be square root of 9, which is plus or minus 3. So we end up having two vertical asymptotes. One is x is equal to 3, and the other is x is equal to negative 3. Are there going to be horizontal asymptotes? In this case, yes, the numerator degree and denominator degree. Are equal, which would mean y equals 0 is the horizontal asymptote. In other words, it is the x-axis. Clearly, we're not going to have a slant asymptote because the numerator degree has to be one unit higher than the denominator degree. So no slant asymptotes here. So let's see if we can do something with this. We know that there is a vertical asymptote at x is equal to negative 3 and x is equal to positive 3. And we also know that the intercept, the y-intercept, is at negative 2 over, it's 0. So the function has to cross here. The x-intercept is at negative 2 over 9. So negative 2 over 9 it's about 0.18. So perhaps it's right here. I did some bad algebra. That is 0. I knew something was off when I came down to the graph. That's certainly bad algebra. 2 times 0 squared is not going to give us negative 2 over 9. For some reason, I have my zeros and ones crossed today. So the x-intercept is 0 and the y-intercept is also 0. In other words, we have it right here. And is there a horizontal asymptote? There is. So the horizontal asymptote is the x-axis. No slant asymptotes. So let's just see what happens. Let's pick an easy number. Let's pick f of minus 1. And that gives us 2 times negative 1 squared over negative 1 squared minus 9. 2 divided by 1 minus 9. 2 over negative 8. We have negative 1 over 4, which is right over here. since it is symmetric, there will be a value there as well. And let's plug in f of -2, which should be 2 times -2 squared, -2 squared minus 9, 8 divided by 4 minus 9, 8 over -5, and that would give us -1.6. So it ends up being right here, -1.6 there, and -1.6 and there, because of symmetry. So we can take care of the middle part right away. In a sense, the function has to go along the asymptote, so it is going up there. It is going to touch the axis and turn and come down. So you can see that things are symmetric. Now, naturally, we have a horizontal asymptote according to number 5. And y equals 0 is the horizontal asymptote. So the question now is, should the function go that way, here, or should it go that way? If we figure this one out, the other side would be pretty straightforward. So let's see. Let's pick an easy number. Let's say -4. Two times -4 squared divided by -4 squared minus 9, which is 2 times 16 over 16 minus 9. That would be 32 over 7. That is 4.1 or 4.2. So it would be perhaps right here. And because of symmetry, we need to have the same value over there. Let's pick another number. I am betting that the curve has to go down toward the x-axis. We will see. F of -5 would be 2 times -5 squared divided by -5 squared minus 9. That is 50 divided by 25 minus 9. We get 16. And that would be equal to 25 over 8. So that is 3.125. So at -5, we end up coming there. So because of symmetry, we would have the same over there. So since we have a vertical asymptote, the function has to go that way. Since there is a horizontal asymptote, the function has to go that way. So we draw it out. That's what it should look like because of symmetry. So that is how we graph based on the asymptotes, vertical asymptotes and horizontal asymptotes, etc. So that's how we sketch a rational function. Mind you, it takes a lot of practice to draw a rational function without using a calculator. We have 7 steps and we have to be excessively careful. So here is another example. The very first step, we've got to determine symmetry. Let's try f of -x. which would give us 2 times negative x minus 1 divided by negative x minus 1, negative 2x minus 1 divided by minus x minus 1. There is a minus 1 in common in the numerator, so we have 2x plus 1, and negative 1 is common in the denominator, so we have x plus 1. Negatives go away, we have 2x plus 1 over x plus 1. That is neither equal to f of x, nor is it equal to negative f of x. So there is no symmetry at all. Let's find the x-intercept. Oh, the 7th step says y-intercept first, so I'll just stick with that. So x is equal to 0. We get 1. And the 3rd step is to find the x-intercept, so we set y is equal to 0. Which would imply 2x minus 1 is equal to 0, and x would be equal to 1 over 2. Step 4, over here, we want to find the vertical asymptote. So how do we find the vertical asymptote? We set denominator equal to 0 and solve for x. So that would be our vertical asymptote. Step 5, horizontal asymptotes. The numerator degree is equal to the denominator degree. It is 1 there and 1 there. So the horizontal asymptote is y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. We get 2. So the numerator degree has to be greater than the denominator degree by exactly 1 for us to have a slant asymptote. So no slant asymptote because the numerator degree and the denominator degree are equal. And lastly, we have to sketch it. So first, let's draw the asymptotes. So the horizontal asymptote is at y equals 2. The vertical asymptote is at x equals 1. The intercept on the y-axis is 1. The intercept on the x-axis is 1. No, it's 1/2. So right there. So that being said, the function has only one way to go because it has to follow that asymptote down that way, and it has to follow that asymptote because it is the horizontal asymptote. And since we have the horizontal asymptote, the vertical asymptote, the function has to go that way because we can't have more than one y-intercept. We can't have more than one x-intercept. So that said, well, in this problem, so that said, this curve right here has to be of that shape because in this problem we have only one x-intercept. So are we correct? Did we do this right? So let's just see. I think we are right. So let's plug in 2, f of 2. It's 2 times 2 minus 1 divided by 2 minus 1. Because the function is 2x minus 1 over x minus 1. 4 minus 1 over 1, we get 3. So f of 2 is 3. And f of 4 is 2 times 4 minus 1 divided by 4 minus 1. That is 7 divided by 3. That is 2 point something. So clearly it is going in a downward trajectory. So we are right on that side. And we already knew that the y-intercept was right here. X-intercept is right there. So there is only one way for the curve to go, and it has to be like so because the function has to go along the asymptotes. So that is how you draw rational functions, and it takes a lot of practice and it is easy to make mistakes, so just be careful.